A satellite, or artificial satellite, is an object, typically a spacecraft, placed into orbit around a celestial body. Satellites serve numerous functions, such as communication relay, weather forecasting, navigation, e.g., GPS, broadcasting, scientific research, and Earth observation. They also have military applications, including reconnaissance, early warning, signals intelligence, and potential weapon delivery. Some satellites include spent rocket stages that deployed them into orbit or satellites that have since become defunct. Most satellites, except passive ones, have onboard power systems such as solar panels or radioisotope thermoelectric generators, RTGs, to generate electricity. Communication with ground stations is typically facilitated by transponders. To reduce costs and complexity, many satellites use a standardized design known as a satellite bus, with CubeSats being particularly popular for their small size. Multiple satellites can operate together as constellations. Due to the high cost of launching, satellites are designed to be lightweight and durable. Communication satellites often function as orbiting radio relay stations, equipped with numerous transponders that provide bandwidths of tens of megahertz. Satellites are launched from the surface into orbit by launch vehicles, positioned at altitudes sufficient to prevent atmospheric orbital decay. They can adjust or maintain their orbits using propulsion systems, typically chemical or ion thrusters. As of 2018, approximately 90% of Earth's satellites were in low Earth orbit or geostationary orbit, with geostationary satellites appearing stationary relative to a fixed point on Earth. Some imaging satellites opt for Sun-synchronous orbits to scan the globe under consistent lighting conditions. The growing number of satellites and space debris has increased the risk of collisions. While most satellites orbit Earth, some orbit other celestial bodies such as the Moon, Mars, or the Sun, and a few follow complex paths, like halo or Lissajous orbits. Earth observation satellites collect data for reconnaissance, mapping, and monitoring weather, oceans, and forests. Space telescopes leverage space's near-perfect vacuum to observe the universe across the electromagnetic spectrum. Communication satellites can relay information over vast distances, reaching remote locations. Satellite navigation systems, like GPS, use predictable orbits and signal delays to provide accurate positioning. Space probes are satellites designed for robotic exploration beyond Earth, while space stations are essentially inhabited satellites. The first artificial satellite, Sputnik 1, was launched by the Soviet Union on October 4, 1957. As of December 31, 2022, there were 6,718 operational satellites in Earth's orbit, with 4,529 belonging to the United States, 3,996 of which are commercial, 590 to China, 174 to Russia, and 1,425 to other countries. The concept of artificial satellites dates back to Isaac Newton's 1687 thought experiment, Newton's cannonball, which explained the motion of natural satellites in Philosophiae Naturalis Principia Mathematica. Fictional depictions appeared later, including Edward Everett Hale's The Brick Moon, 1869, and Jules Verne's The Begum's Fortune, 1879. Konstantin Tsiolkovsky's 1903 work, exploring space using jet propulsion devices marked the first serious study of rocketry for launching spacecraft, calculating necessary orbital speeds and advocating for multi-stage rockets. Herman Potarchnik's 1928 book, The Problem of Space Travel explored peaceful and military satellite applications, describing geostationary orbits and radio communication, but did not predict mass broadcasting. In 1945, Arthur C. Clarke proposed using geostationary satellites for global communication, suggesting a network of 3 satellites. The U.S. Air Force's Project RAND in 1946 highlighted satellites' scientific potential in its report, preliminary design of an experimental world-circling spaceship **, though it viewed satellites more as scientific and political tools than military assets. Lyman Spitzer proposed the idea of an orbiting space telescope in 1946. By 1954, Project RAND's publication Scientific Uses for a Satellite Vehicle * by R. R. Carhart and the subsequent 1955 work by H. K. Kalman and W. W. Kellogg further elaborated on satellites' scientific applications. The Soviet Union launched the first artificial satellite, Sputnik 1, on October 4, 1957, marking the start of the space race during the Cold War, led by chief designer Sergei Korolev. Sputnik 1 gathered atmospheric data and studied radio signals in the ionosphere. The U.S., already planning satellite launches under Project Vanguard for the International Geophysical Year, 1957-1958, was spurred into action by Sputnik's success. Sputnik 2 followed on November 3, 1957, carrying the first living creature, Laika the dog, into orbit. The U.S. launched its first satellite, Explorer 1, on January 31, 1958, which discovered the Earth's Van Allen radiation belts. NASA's TIROS 1, launched on April 1, 1960, provided the first space-based weather images. By mid-1961, the U.S. Space Surveillance Network had catalogued 115 satellites. Canada, Australia, and Italy launched satellites with U.S. assistance, while France became the third country to independently launch a satellite, Asterix, on November 26, 1965, using its own Diamant, a rocket from Algeria. Early satellites were custom-built, but advancements in technology led to standardized satellite designs called satellite buses, with the first being the HS-333 geosynchronous satellite launched in 1972. In 1997, Free Flyer software was introduced for satellite mission planning and operations. By the late 2010s, the launch and operational use of large satellite internet constellations caused the number of active satellites to more than double within 5 years, leading to planned deorbiting processes for end-of-life satellites to meet regulatory requirements. The International Space Station is the largest artificial satellite. With the rise of CubeSats and increased launches of microsatellites, satellites in low Earth orbit, LEO, were designed to break up and burn in the atmosphere at the end of their operational life. For instance, SpaceX's Starlink satellites are built to completely burn upon re-entry. Many nations, including the US, Russia, China, India, and others, have launched satellites. Japan's JAXA and NASA are collaborating on LingoSat, a wooden satellite prototype set to launch in 2024. The project began with tests of wood samples in space in 2021 to examine the material's durability in space conditions. Satellites use chemical or ion propulsion systems for orbital adjustments and reaction wheels to control orientation. Earth-orbiting satellites face challenges from Earth's magnetic and gravitational fields and solar radiation, while those further out contend more with gravitational effects from the Moon and Sun. Protective ultra-white coatings shield satellites from UV radiation. Without precise orbit and attitude control, satellites cannot maintain communication with ground stations. Chemical thrusters on satellites often use hypergolic propellants, like hydrazine-based monopropellants or monomethylhydrazine dinitrogen tetroxide mixtures, which ignite spontaneously upon contact. Ion thrusters, typically Hall-effect thrusters using xenon, provide more fuel-efficient propulsion but produce low thrust, around 0.5 N, necessitating longer operational durations. Satellites primarily use solar panels for power, with radioisotope thermoelectric generators used in deep space missions with limited sunlight. Solar panels are connected with slip rings that allow rotation to maximize power generation by facing the sun directly. Satellites also require batteries to store energy for use during periods without sunlight, such as when inside a launch vehicle or during night. The most common satellite batteries today are lithium-ion, while older models used nickel-hydrogen batteries. Earth observation satellites are used for remote sensing to monitor Earth, with most placed in low Earth orbit for high-resolution data, and some in geostationary orbit for continuous coverage. Sun synchronous orbits provide consistent lighting. These satellites are equipped with various instruments and are used in fields like archaeology, cartography, environmental monitoring, meteorology, and reconnaissance. Over 950 such satellites existed by 2021, with Planet Labs operating the most. Weather satellites track meteorological phenomena, while environmental monitoring satellites observe vegetation, atmospheric gases, sea states, and ice. Communication satellites relay and amplify telecommunication signals, enabling services like TV, radio, and Internet. These often operate in geostationary orbits or low Earth orbit constellations. Communication satellites use regulated radio and microwave frequencies to avoid signal interference. Spy satellites are specialized Earth observation or communication satellites used for military purposes, such as missile warning, reconnaissance, and surveillance. Navigational satellites transmit radio signals to ground receivers, enabling precise location determination with accuracies of a few meters. Experimental satellites *. These include tether satellites connected by cables, recovery satellites that return payloads to Earth, biosatellites for scientific experiments involving living organisms, and proposed space-based solar power satellites that would collect and transmit solar energy. Weapon satellites *. Satellites have been hacked by militant groups for propaganda and data theft. Several countries, including the US, Russia, China, and India, have demonstrated capabilities to destroy satellites using ballistic missiles. Notable incidents include China destroying an old weather satellite in 2007 and the US shooting down a defunct spy satellite in 2008. India joined this group in 2019 by successfully destroying a satellite in low Earth orbit. The environmental impact of satellites is becoming a concern due to the rapid increase in satellite launches. Key issues include resource use and atmospheric pollution during various satellite lifecycle stages. Launch emissions. Rocket launchers release pollutants such as black carbon, CO2, NOx, aluminium, and water vapor, particularly affecting the upper atmosphere. Pollutants like NOx and black carbon can cause warming and alter stratospheric circulation, affecting ozone levels. However, current launch rates would need to increase tenfold to match the impact of regulated ozone-depleting substances. Low Earth orbit (LEO) satellites contribute various pollutants to the upper atmosphere during their life cycle. Repositioning uses hydrazine as a propellant, emitting gases like ammonia and nitrogen. Material degradation due to atomic oxygen leads to emissions of CO2 and CO as insulation materials like Captain degrade. Night sky impact. The increasing number of satellites may raise night sky brightness by up to 10%, potentially disorienting wildlife that navigates using celestial cues and affecting cultural connections to nature. Ground infrastructure. Monitoring satellites requires substantial infrastructure with significant but not yet quantified environmental impacts. End-of-life concerns. Uncontrolled deorbits pose risks of pollution. Notable failures include Cosmos 954. Satellites moved to graveyard orbits or intentionally deorbited create long-term space debris. Most satellites burn up on re-entry, releasing pollutants and potentially impacting the ozone layer and Earth's albedo, raising concerns about unintentional geoengineering. About 70% of deorbited satellites end up in the ocean without recovery. Space debris presents significant risks to spacecraft and satellites in geocentric orbits, with the potential to trigger a Kessler syndrome, which could hinder future space exploration. The rise of satellite constellations, like SpaceX's Starlink, has led to increased orbital pollution, which the astronomical community, including the International Astronomical Union (IAU), has warned about. A 2020 SATCON1 workshop report highlighted that large satellite constellations could severely disrupt astronomical research and proposed 6 mitigation strategies. The IAU is establishing a center to coordinate efforts to reduce these impacts. Additionally, satellite transmissions, particularly those from GPS satellites, are vulnerable to jamming by land-based transmitters. This interference is typically limited to the range of the jamming signal but can affect satellite phone and television services. Geostationary satellites are also at risk from misused frequencies or incorrect timing by Earth stations, which can disrupt satellite transponders. Advanced monitoring tools are now in place to help satellite operators manage and mitigate these issues.